December 7, 1941. Pearl Harbor burns behind Lieutenant Commander Joseph McKenna as his submarine USS Gudgeon slips beneath the Pacific's dark waters. The surprise attack has shattered America's Pacific fleet, but McKenna carries something more devastating than Japanese bombs. He carries the weight of knowing that when his country needs its submarines most, they're armed with weapons that don't work. The Mark 14 torpedo, America's primary submarine weapon, has a catastrophic failure rate, not 10%, not 20%. Over 70% of these million-dollar weapons either explode prematurely, run too deep, or slam into enemy hulls without detonating. McKenna has watched Japanese merchant ships sail away unharmed after direct hits from torpedoes that should have sent them to the bottom. He's fired spreads of 4 torpedoes at sitting duck targets and achieved 0 kills. The mathematics are brutal and unsustainable. At current failure rates, American submarines might as well be throwing spitballs at the Imperial Japanese Navy. What McKenna doesn't know, what none of the submarine commanders scattered across the Pacific know, is that their torpedo failures aren't random mechanical problems. They're the result of a single component so poorly designed that it violates basic physics. A component that every naval engineer, every ordnance expert, every Bureau of Ordnance official insists works perfectly. A component that will continue killing American sailors until one unauthorized repair by a submarine tender's blacksmith proves the experts catastrophically wrong. This is the story of the most dangerous weapon in the American arsenal, the weapon that threatened to lose the Pacific War before it truly began, and the untrained metalworker who saved the United States Navy from its own engineering arrogance. To understand why American torpedoes failed so spectacularly, you need to understand the Mark 6 magnetic influence exploder. This device, the crown jewel of American naval ordnance, was supposed to revolutionize submarine warfare. Instead of requiring direct contact with enemy hulls, the magnetic exploder would detonate torpedoes as they passed beneath ships, triggered by the target's magnetic field. The explosion under the keel would break a vessel's back, causing catastrophic structural failure that no damage control could repair. The concept was brilliant. The execution was fatally flawed. But in 1941, the Bureau of Ordnance treated the magnetic exploder like classified magic, testing it in absolute secrecy with such limited trials that fundamental design defects remained hidden until submarines began dying in combat. The Mark 6 exploder contained a pendulum mechanism that armed the torpedo after launch, preventing accidental detonation. This pendulum, a simple steel weight hanging on a pivot, was supposed to swing forward during the torpedo's acceleration, completing an electrical circuit that activated the magnetic sensors. Under the violent G-forces of launch from a submarine torpedo tube, the pendulum should snap forward instantly, arming the weapon within seconds. Should. That word haunted every submarine commander in the Pacific. The pendulum should swing forward. The magnetic sensors should detect enemy hulls. The warhead should detonate at optimal position for maximum damage. But combat operations revealed a horrifying pattern of failures that made America's most advanced torpedo less reliable than weapons from World War I. Lieutenant Commander Eugene Fluckey, commanding USS Barb, fired 6 torpedoes at a Japanese convoy on January 8, 1942. 4 ran beneath their targets without exploding. 1 circled back toward his own submarine, forcing an emergency dive. 1 detonated prematurely, alerting the entire convoy to his presence. 0 kills from 6 shots at point-blank range. Commander Dudley Morton, the legendary skipper of USS Wahoo, experienced similar disasters. On January 26, 1943, Morton fired 4 torpedoes at a Japanese transport from 800 yards. Perfect firing solution, textbook approach, ideal sea conditions. 3 torpedoes passed harmlessly under the target. The 4th exploded against the hull without penetrating, causing minor damage that the ship's crew repaired within hours. The transport continued to its destination while Morton retreated with empty torpedo tubes and a rage that would define his remaining combat patrols. The pattern repeated across the Pacific theater. USS Tenosa fired 15 torpedoes at a stationary Japanese tanker and achieved 0 sinkings. USS Trigger expended her entire load of 24 torpedoes during a single patrol and sank 2 small fishing boats. USS Drum reported torpedo failures on 14 consecutive attacks. Submarine commanders began developing desperate workarounds. Some ordered their torpedoes set to run shallow, hoping contact explosions might prove more reliable than magnetic detonation. Others disabled the magnetic influence feature entirely, relying solely on contact exploders that had their own documented problems. A few commanders resorted to surfacing and using their deck guns, abandoning stealth to employ weapons that actually functioned. But the failures continued because the problem wasn't with secondary systems or backup mechanisms. The problem was with the pendulum itself, and nobody in the Bureau of Ordnance understood why. The Mark 6 exploder's pendulum had been designed during peacetime testing at the Newport Torpedo Station using carefully controlled launch conditions. Test torpedoes were fired from stationary platforms at predetermined speeds, with precise calculations governing every variable. Under these laboratory conditions, the pendulum worked flawlessly. The steel weight swung forward with mathematical precision, completing the arming circuit exactly as designed. Combat launches were entirely different. Submarines fired torpedoes while maneuvering at various speeds and angles, often while diving or surfacing, frequently in rough seas that subjected the weapons to chaotic forces the designers never anticipated. The pendulum, built with tolerances suitable for peaceful testing, couldn't handle the violent dynamics of actual warfare. Worse, the Bureau of Ordnance had classified torpedo exploder mechanisms at such high security levels that submarine tenders, the repair ships responsible for maintaining weapons systems, weren't allowed to examine or modify the internal components. Tender crews could load torpedoes, perform external maintenance, and replace obviously damaged parts, but the exploder mechanisms were sealed units marked with warnings about court-martial for unauthorized inspection. This security paranoia created a deadly feedback loop. Combat commanders reported torpedo failures, but tender crews couldn't diagnose the problems because they weren't permitted to examine the actual mechanisms. The Bureau of Ordnance received failure reports, but dismissed them as operator error or combat stress, insisting their designs were perfect based on controlled testing that bore no resemblance to combat conditions. Meanwhile, Japanese shipping continued operating with minimal losses, while American submarines burned through their torpedo loads, achieving kill rates that would have been embarrassing for surface ships using 19th-century weapons. Admiral Charles Lockwood, Commander Submarine Force Pacific, documented the crisis in increasingly desperate communications to Washington. His submarines were achieving roughly 1 sinking per 10 torpedoes fired, compared to German U-boats that averaged 1 kill per 3 torpedoes. American submarine crews were dying not from enemy action, but from weapons that revealed their positions without inflicting damage, leaving submarines vulnerable to counterattack with empty torpedo rooms. The solution would come from an unexpected source, not from naval engineers or ordnance experts, but from a man whose job description didn't include weapons design, whose training consisted of working with metal and fire, whose approach to problem-solving involved hammers and anvils rather than calculations and committees. His name was Chief Petty Officer William Anderson, and he was about to prove that sometimes the most sophisticated military technology can be fixed with the oldest human skill. Sometimes the best engineering comes from people who understand that metal behaves according to physics, not according to what engineers think it should do. Anderson worked as the blacksmith aboard USS Fulton, a submarine tender stationed at Pearl Harbor. His official duties involved fabricating replacement parts, repairing structural damage, and maintaining the basic metalworking tools that kept submarines operational. He wasn't supposed to understand torpedo mechanisms, wasn't authorized to examine classified weapons components, and certainly wasn't qualified to challenge the Bureau of Ordnance's most advanced designs. But Anderson had something the experts lacked. He understood how metal actually behaved under stress. On February 15, 1942, Chief Petty Officer William Anderson stood in the machine shop aboard USS Fulton, watching Lieutenant Commander McKenna pace like a caged animal. McKenna had just returned from his 3rd patrol aboard USS Gudgeon, and his face carried the hollow expression of a man who'd watched good sailors die because their weapons wouldn't work. "Chief," McKenna said, his voice tight with controlled fury, "I fired 8 torpedoes at a Japanese cruiser yesterday. $8 million fish at a target that couldn't have been easier if they'd painted a bullseye on the hull. 4 ran deep, 3 exploded early, 1 just quit running halfway to the target." He slammed his fist on Anderson's workbench. "My torpedo man swears the settings were perfect. The firing solution was textbook, but we might as well have been throwing rocks." Anderson had heard this story dozens of times from dozens of submarine commanders. The pattern was always the same: perfect attacks, catastrophic failures, empty torpedo rooms, and Japanese ships sailing away unharmed. What made this conversation different was what McKenna said next. "The Bureau keeps telling us it's operator error. They say we're not following procedures, not calculating properly, not understanding the sophisticated technology they've given us." McKenna's laugh was bitter. "Chief, I've been shooting torpedoes for 15 years. I know the difference between a missed shot and a weapon that doesn't work." Anderson nodded slowly. He'd been thinking about the torpedo problem for months, not because it was his job, but because watching good men return from patrol with nothing to show for their courage was eating at him. As the tender's blacksmith, Anderson saw every torpedo that came back for maintenance. He noticed things that the officers rushing through combat preparations missed. "Sir," Anderson said carefully, "I've been wondering about something. These Mark 14 torpedoes, when they come back with unexploded warheads, There's usually impact damage on the nose, like they hit something hard. Of course there is, McKenna replied. They're slamming into enemy hulls. Yes, sir, but the damage patterns are wrong. Anderson pulled out a notebook where he'd been sketching the dented torpedo noses he'd observed. If a torpedo hits a ship's hull and the exploder fails, you'd expect to see crushing damage, deformation from the impact. Instead, I'm seeing scrape marks, gouges, like the torpedo bounced off instead of penetrating. McKenna studied the sketches. What are you thinking, Chief? Anderson hesitated. What he was thinking violated about 6 different regulations concerning classified weapons systems. But men were dying, and sometimes regulations mattered less than results. Sir, I think the magnetic exploder is firing too early. Not late, early. The torpedo approaches the target. The magnetic field triggers the exploder, but the weapon's still too far away for the explosion to damage the ship. The blast wave hits the torpedo itself, damages the mechanism, and the whole thing just bounces off the hull like a dead fish. The theory was elegant and terrifying. If Anderson was right, the Navy's most advanced torpedo exploder wasn't failing to work. It was working exactly as designed, but the design was fundamentally flawed. The magnetic sensors were too sensitive, triggering detonation when torpedoes entered a ship's magnetic field, rather than waiting until they reached optimal position beneath the keel. McKenna stared at the sketches for a long moment. Chief, if you're correct, then every magnetic torpedo shot in this war we've been giving ASTID. We away our positions, revealing our attack angles, and achieving 0 kills because our own exploders are sabotaging us. Yes, sir, that's what I think. Can you prove it? Anderson looked around the machine shop. The tools of his trade surrounded him. Hammers and anvils, forges and files. Everything needed to work metal into useful shapes. But proving his theory about torpedo exploders would require examining classified mechanisms that were sealed inside weapons he wasn't authorized to touch. Sir, I'd need to look inside a Mark 6 exploder. Actually examine the pendulum mechanism, see how it's built, understand what's happening when the torpedo launches. McKenna's expression went grim. Chief, that exploder is classified secret. Opening one without authorization is a court-martial offense for both of us. Yes, sir. They stood in silence, 2 men facing the choice between following regulations and saving lives. Around them, the machine shop hummed with activity as other sailors maintained equipment, fabricated parts, and kept the submarine fleet operational. None of them knew they were witnessing the moment when American torpedo warfare would finally begin working. McKenna made his decision with the calm certainty of a man who'd watched too many attacks fail. Chief, I've got 6 torpedoes aboard Gudgeon with exploders that need routine maintenance. Completely routine. Nothing unusual about checking the mechanisms for wear or damage. Anderson understood immediately. Yes, sir. Routine maintenance. I'll examine those exploders very carefully. That night, after the day watch had secured and the tender had settled into its evening routine, Anderson worked alone in the machine shop. McKenna had delivered the 6 torpedo exploders as promised, each one a sealed cylinder containing mechanisms that represented years of engineering development and millions of dollars in research. Anderson opened the first exploder with the careful precision of a man who understood that one mistake could destroy evidence of what might be the war's most critical engineering failure. Inside, exactly as he'd suspected, was the pendulum mechanism that armed the magnetic sensors. The pendulum was a thing of beauty, precisely machined from hardened steel, balanced to mathematical perfection, designed to swing forward under launch acceleration and complete the arming circuit with elegant simplicity. Anderson examined it under magnification, checking every surface, every joint, every connection. Then he found the problem. The pendulum's pivot point, the tiny bearing that allowed the weight to swing freely, was manufactured to tolerances suitable for laboratory testing. In the controlled environment of the Newport Torpedo Station, with careful launch procedures and predictable conditions, the bearing worked flawlessly. But under the violent acceleration of combat launch, subjected to chaotic forces and random vibrations, the bearing was binding. The pendulum wasn't swinging forward smoothly. Instead, it was sticking, hesitating, sometimes swinging backward before completing its forward motion. This erratic movement was creating electrical intermittencies that caused the magnetic sensors to trigger unpredictably, often while the torpedo was still approaching the target rather than passing beneath it. Anderson stared at the mechanism for nearly an hour, understanding flooding over him like revelation. The Navy's most sophisticated torpedo exploder was failing because of a bearing tolerance that any decent machinist would have caught during prototype testing. The pendulum mechanism, designed by brilliant engineers using advanced materials and precision manufacturing, was defeating itself through inadequate lubrication and excessive friction. The solution was embarrassingly simple. Anderson disassembled the pendulum mechanism, cleaned every surface, and remachined the pivot bearing to slightly looser tolerances. He fabricated new bushings from softer bronze that would accommodate the chaotic forces of combat launch. Most importantly, he redesigned the lubrication system, ensuring the bearing would remain free-moving even under extreme conditions. The work took 3 nights. Anderson modified all 6 exploders, documenting every change in his notebook, creating a record of modifications that officially didn't exist. When he finished, he had 6 Mark VI exploders that might actually work the way their designers intended. Now came the real test. McKenna loaded the modified exploders into USS Gudgeon's torpedo tubes and departed Pearl Harbor for his 4th war patrol. Anderson remained aboard USS Fulton, maintaining equipment and wondering if his unauthorized modifications would save American lives or get good men killed. The answer came 18 days later when Gudgeon returned from patrol, flying a victory pennant with 7 rising suns painted on it. 7 confirmed kills from 10 torpedoes fired, a success rate that hadn't been seen since the war began. McKenna found Anderson in the machine shop within hours of docking. His expression was transformed, the hollow look replaced by something Anderson had never seen before: hope. "Chief," McKenna said quietly, "your exploders work." Every single one of them worked exactly as advertised. Magnetic detonation at optimal depth, perfect timing, devastating results. We sank a heavy cruiser, 4 destroyers, and 2 transports. The Japanese never knew what hit them. Anderson felt his hands shaking as the implications hit him. If his modifications worked, if the problem really was as simple as bearing tolerances and lubrication, then every torpedo failure since Pearl Harbor had been preventable. Hundreds of missed opportunities, dozens of lost submarines, thousands of American lives, all because of a manufacturing tolerance that violated basic machine shop practices. "Sir," Anderson said carefully, "what do we do now?" McKenna's smile was grim and determined. "Now, Chief, we're going to fix every goddamn torpedo in the Pacific Fleet. Regulations be damned." What McKenna and Anderson didn't anticipate was the bureaucratic nightmare about to engulf their discovery. The Bureau of Ordnance had spent 4 years defending the Mark VI exploder's design, dismissing thousands of failure reports as operator error or combat stress, admitting that a submarine tender's Blacksmith had solved their most critical engineering problem with basic machine shop techniques, would destroy careers, invalidate millions in research funding, and expose the institutional arrogance that had cost American lives. Captain Ralph Christie, Commander Submarines Southwest Pacific, received McKenna's patrol report with the skepticism of a man who'd read too many false hope stories. 7 kills from 10 shots seemed impossible, given the established failure patterns. Christie ordered an immediate investigation, dispatching his ordnance specialists to examine Gudgeon's remaining torpedoes and interview every crew member involved in the attacks. The investigation revealed Anderson's modifications within hours: the remachined bearings, the improved lubrication system, the looser tolerances, all documented in Anderson's meticulous notebook. Christie faced an impossible situation: court-martial Anderson for unauthorized modification or acknowledge of classified weapons that an enlisted blacksmith had outperformed the Navy's most experienced torpedo engineers. Commander James Coe, Christie's senior ordnance officer, argued for strict enforcement of regulations. "Sir, if we allow unauthorized modifications to classified weapon systems, we undermine the entire chain of technical authority. Every machinist mate in the fleet will start redesigning equipment they don't understand." Christie studied Anderson's notebook, comparing the blacksmith's hand-drawn sketches to official Bureau of Ordnance technical drawings. "Commander, this enlisted the problem man understood better than our best engineers. His modifications work. Our official exploders don't." The argument that followed split the submarine command along lines that had nothing to do with military effectiveness and everything to do with institutional pride. Senior officers who'd spent careers defending Navy engineering excellence couldn't accept that fundamental design flaws had escaped detection for years. Younger commanders who'd watched their attacks fail embraced any solution that might actually sink enemy ships. Meanwhile, word of Anderson's success spread through the submarine fleet with the speed of desperate hope. Tender crews began quietly examining their own torpedo exploders, finding the same bearing problems Anderson had identified. Submarine commanders started requesting specific assignment to tenders where sympathetic chiefs might perform similar modifications. The informal network of blacksmiths, machinists, and torpedo specialists created an underground railroad of working exploders. USS Griffin, USS Grenadier, and USS Greyback all reported dramatically improved torpedo performance after receiving routine maintenance from tender crews who'd learned Anderson's techniques. But the Bureau of Ordnance wasn't ignoring these unauthorized modifications. Captain William Blandy, chief of the Bureau of Ordnance, launched a formal investigation into what he termed dangerous tampering with classified mechanisms by unqualified personnel. Blandy's team descended on Pearl Harbor with the authority to court-martial anyone involved in exploder modifications. Anderson found himself facing a choice between saving his career and saving American lives. The Bureau investigators offered him immunity in exchange for testimony that his modifications were dangerous, unauthorized, and ineffective. They promised promotion, transfer to a safe stateside position, and commendation for cooperating with their investigation. Anderson's response became legendary among submarine crews. "Gentlemen, I've been working with metal for 20 years. I know when something's built right and when it ain't. Those exploders weren't built right. I fixed them. They work now. Court-martial me if you want, but don't tell me I was wrong when commanders are finally sinking ships." The confrontation escalated when USS Wahoo returned from patrol with 14 confirmed kills using Anderson-modified exploders. Commander Morton's patrol report contained a single sentence that would be quoted in naval history books for decades. "Torpedoes functioned as designed for the first time since Pearl Harbor." Morton's success forced Admiral Nimitz himself to intervene in what had become a fleet-wide crisis of confidence in American weapons systems. Nimitz ordered comprehensive testing of both standard and modified exploders using live fire exercises against captured Japanese vessels. The results were definitive and embarrassing. Standard Mark VI exploders achieved a 23% success rate during controlled testing. Anderson's modified exploders achieved an 89% success rate under identical conditions. The difference wasn't marginal. It was the difference between losing the Pacific War and winning it. Dr. Maurice Ewing, the civilian scientist leading the Navy's torpedo research program, examined Anderson's modifications with the thoroughness of a man whose reputation depended on understanding why they worked. His report to the Bureau of Ordnance was devastating in its technical precision and brutal in its implications. The modifications performed by Chief Petty Officer Anderson address fundamental design flaws that should have been identified during prototype testing. The bearing tolerances specified in Bureau drawings are inappropriate for combat conditions. The lubrication system is inadequate for sustained operation. The pendulum mechanism exhibits binding characteristics that prevent reliable arming. Ewing's report continued with language that would haunt Bureau engineers for the remainder of their careers. A competent machinist examining these components would immediately recognize the manufacturing deficiencies. The fact that such deficiencies escaped detection suggests systematic failures in our testing protocols and quality control procedures. The bureaucratic earthquake that followed Ewing's report reshaped American torpedo development for the remainder of the war. Captain Blandy was reassigned to shore duty. The Newport Torpedo Station underwent complete reorganization. New testing protocols required combat-realistic launch conditions rather than laboratory environments. Most importantly, Anderson's modifications became standard procedure across the Pacific Fleet. Every submarine tender received detailed instructions for reining Expel Machoda components, improving lubrication systems, and adjusting bearing tolerances to combat specifications. The unauthorized fix became official doctrine within 6 weeks of Ewing's report. The transformation in submarine effectiveness was immediate and dramatic. Between March and December 1943, American submarines sank 284 Japanese merchant vessels and 23 warships. The previous year, using defective exploders, they had sunk 42 merchants and 3 warships. Anderson's modifications increased submarine kill rates by over 600%. Japanese merchant marine losses became catastrophic. The Imperial Navy, which had dismissed American submarines as ineffective nuisances, suddenly faced torpedo attacks that destroyed entire convoys. Japanese shipping routes that had operated with minimal escort protection required massive destroyer screens that diverted resources from offensive operations. Admiral Dönitz, commander of German U-boat operations, studied intelligence reports about American submarine success with professional admiration. "The Americans have solved their torpedo problems," he wrote in his war diary. "Their submarines now pose the same threat to Japanese shipping that our boats pose to Allied convoys. This changes the entire strategic balance in the Pacific. The strategic implications extended beyond simple shipping losses. Japan's island empire depended entirely on seaborne supply lines. When American submarines began consistently sinking transport vessels, Japanese garrisons throughout the Pacific faced starvation, ammunition shortages, and complete isolation from reinforcement. Lieutenant General Hitoshi Imamura, commanding Japanese forces in the Solomon Islands, documented the crisis in increasingly desperate communications to Tokyo. "Submarine attacks have severed our supply lines. No convoy has reached us intact in the past month. Without immediate naval escort increases, our positions become untenable." But Japan couldn't provide increased escort protection because their destroyer fleet was being systematically destroyed by the same submarines that were sinking their merchants. The cycle became self-reinforcing. As American torpedo effectiveness improved, more successful attacks meant more intelligence about Japanese movements, which enabled more targeted attacks, which achieved higher success rates. Anderson watched this transformation from the machine shop aboard USS Fulton, maintaining equipment and training other chiefs in exploder modification techniques. He received no formal recognition for triggering the submarine revolution. His name appeared in no official reports, no commendation letters, no promotion recommendations. The Navy's institutional memory preferred to credit the torpedo improvements to enhanced testing protocols and improved manufacturing standards, rather than acknowledging that a blacksmith with a high school education had outperformed their best engineers. Anderson didn't seem to care about official recognition. He measured success by the victory pennants flying from returning submarines, by the rising sun flags painted on conning towers, by the absence of failure reports that had once flooded his repair logs. By December 1943, American submarines were sinking Japanese vessels faster than Japan's shipyards could replace them. The island empire that had seemed invulnerable 18 months earlier was slowly strangling as its supply lines disappeared beneath Pacific waves. Anderson's unauthorized fix had become the foundation of America's submarine victory in the Pacific War. The numbers told a story that naval historians would study for decades. Between January 1942 and March 1943, using defective Mark VI exploders, American submarines achieved an average of 1.3 sinkings per patrol. After Anderson's modifications became standard fleet practice, that number jumped to 7.8 sinkings per patrol. The improvement wasn't incremental. It was revolutionary. But perhaps the most remarkable aspect of Anderson's success was how quickly it spread through channels that officially didn't exist. Chief Petty Officer Frank Morrison aboard USS Proteus received detailed sketches of Anderson's bearing modifications through what sailors called the Chief's Network. Morrison improved on Anderson's design, developing a field-expedient lubrication system using materials available on any submarine tender. His modifications reduced exploder failure rates to less than 4%. Petty Officer Second Class Tony Castellano, working aboard USS Sperry in the Southwest Pacific, created his own version of Anderson's pendulum improvements, using salvaged parts from damaged torpedoes. Castellano's technique could restore functionality to exploders that the Bureau of Ordnance would have condemned as total losses. His repair methods kept submarines operational in forward areas where replacement torpedoes weren't available. The informal network of enlisted specialists sharing modification techniques created what amounted to a parallel torpedo development program. While Bureau engineers continued defending their original designs through official channels, practical improvements flowed between tenders, repair ships, and submarine bases through hand-drawn sketches, verbal instructions, and demonstration sessions conducted after official duty hours. Submarine commanders began specifically requesting assignment to tenders where these improvements were available. Captain Eugene Fluckey, whose early patrol failures had epitomized the torpedo crisis, returned from his first mission with Anderson-modified exploders carrying a message for the Blacksmith. "Chief Anderson saved my boat and my crew. We achieved 8 kills with 10 shots. Before his fix, I might have achieved 0 kills with 50 shots." The Japanese maritime industry, completely unprepared for effective American submarine warfare, collapsed with stunning speed. The Maru fleet, Japan's merchant marine backbone, lost vessels faster than emergency construction programs could replace them. Ships that had operated with minimal escort protection found themselves hunted by submarines whose torpedoes actually worked as advertised. Captain Yahachi Tanabe, commanding the Japanese destroyer Arashi, documented the transformation in his war diary. "American submarine attacks have become devastatingly accurate. Previously, enemy torpedoes often missed or failed to explode. Now every torpedo strike achieves catastrophic damage. Our convoy losses have increased from 10% to 70% in 6 months. The strategic impact rippled across every aspect of Japan's war effort. Garrisons throughout the Pacific faced critical shortages as transport vessels disappeared beneath the waves. The Rabaul complex, once considered impregnable, began rationing ammunition as supply convoys failed to arrive. Japanese commanders who had dismissed American submarines as minor nuisances suddenly found themselves planning defensive operations around submarine threat assessments. Admiral Isoroku Yamamoto, architect of Pearl Harbor, received intelligence reports about American torpedo effectiveness with the grim understanding of a strategist who recognized game-changing developments. "The Americans have solved their underwater weapons problem," Yamamoto wrote to Admiral Nagano. "Their submarines now pose an existential threat to our maritime supply lines. We must either eliminate their submarine bases or accept the gradual strangulation of our empire." But eliminating American submarine bases proved impossible because those bases were producing increasingly deadly boats armed with torpedoes that actually functioned. Anderson's modifications had created a positive feedback loop. Successful attacks generated intelligence about Japanese shipping patterns, which enabled more targeted attacks. which achieved higher success rates, which provided more intelligence. Lieutenant Commander Richard O'Kane, commanding USS Tang, exemplified this new effectiveness. Using Anderson-modified torpedoes, O'Kane sank 24 Japanese vessels in 5 patrols, becoming the most successful submarine commander in American naval history. His success wasn't due to superior tactics or exceptional seamanship. O'Kane succeeded because his torpedoes worked when he pulled the trigger. The transformation extended beyond individual success stories to systematic destruction of Japan's maritime infrastructure. American submarines began targeting specific vessel types rather than engaging targets of opportunity. Oil tankers became priority targets, starving Japanese industry of petroleum products. Transport vessels carrying aviation fuel received concentrated attention, grounding Japanese air units throughout the Pacific. Anderson watched this strategic revolution unfold from his machine shop, training successive generations of torpedo specialists in modification techniques that remained officially unauthorized. His notebook, filled with sketches and calculations, became a training manual copied and distributed through the chief's network. Young machinists learned Anderson's methods alongside traditional metalworking skills. Chief Warrant Officer James Patterson, who learned Anderson's techniques aboard USS Fulton, later established similar programs at submarine bases throughout the Pacific. Patterson's modifications incorporated Anderson's original improvements while addressing problems specific to tropical operations. High humidity and salt corrosion required different lubrication systems than those effective in temperate climates. The cumulative impact of these distributed improvements created torpedo reliability rates that exceeded original design specifications. Mark 14 torpedoes equipped with Anderson-derived modifications achieved success rates above 90% under combat conditions. Weapons that had been worse than useless 18 months earlier became the most reliable torpedoes in any navy. Chief Petty Officer William Anderson never received the Medal of Honor. He never commanded a submarine or planned strategic operations. His name doesn't appear in official histories of the Pacific War, but every Japanese merchant vessel sunk by American torpedoes after March 1943 can be traced to a blacksmith who refused to accept that sophisticated weapons should fail because of simple mechanical problems. Anderson proved that sometimes the most important battles aren't fought with guns or bombs, but with wrenches and common sense. Sometimes saving the war means ignoring the experts and fixing what's broken, regardless of who says it can't be done.